Started. Thank you everyone for coming today to this very special SPAAM seminar. We're delighted to be joined by two of our friends from the Oxford SIAM chapter. So first we'll be hearing from Nicholas about online optimization of machine learning collision models to accelerate direct molecular simulation of rarefied gas flows.
Thank you very much. Thank you. Yeah, sorry for the mealy-mouthed title, but my supervisor really did insist on every single one of those words. So yeah, I did try to cut that down a little bit. But thanks very much for having me as well. It's very nice to be back in Warwick, especially now that I've graduated to the big room. Last time I was in the little room for the AMP conference last year, so it's nice to be in the room with a view. And today I'm hoping to talk a little bit about my work trying to accelerate some numerical methods for rarefied gas flows. It's all joined with my supervisor Justin at Oxford and our collaborator John, who is at Notre Dame in the US. So let me give a little bit of motivation, and feel free to stop me at any point with a small audience. It's nice to be stopped rather than have questions at the end. So tell me if I'm not making sense. But the motivation for this work is to use machine learning to speed up some models which are of application in high atmosphere aerodynamics. We normally, for these applications, solve the Boltzmann equation instead of Navier-Stokes, which can be either very expensive or prohibitively expensive, depending on the method you use to solve it. So the very expensive method is to use some kind of experimental data to calibrate a nice simple model to solve. The prohibitively expensive one is to do molecular dynamics, where you're really resolving extremely fine-grained, detailed information about the gas. The method I'm using, or trying to accelerate, lies kind of halfway in between, but it's still very high fidelity and very computationally expensive. So the goal is to speed up this method to get comparable accuracy with machine learning. So we are able to do this, at least for some simple kind of models, simple test cases. Although there are some, whoops, sorry, I tried to use the laser pointer, I made a mistake. Thank you. So yeah, we're able to do this, but we find that some of our machine learning models, if you train them offline in advance on some data set, they're perfectly happy when they're asked to reproduce that data set, but actually in physics applications, we'd like to ask for something a bit more robust and generalizable. And the models, at least that I was able to train, kind of break quite easily when you expose them to new physical conditions. So probably the main contribution to potential engineering applications is these online training methods. We try to generate a new data set during the simulation and do the training kind of alongside the physics. And this can reproduce accuracy for an extremely wide range of physical conditions, but at a much lower cost. And I should apologize that there's going to be, or apologize for the opposite, for the fact that there's absolutely no maths involved in the talk. So please bear with me and wait for Zoe for that. But the little bit of physics background, I suppose, is that you may be familiar or may not be with the fluid dynamics equations, Navier-Stokes equations, which is some quite complicated PDE, which you have to solve for normal fluids, normal gases, which have this Knudsen number relatively small. So this Knudsen number is like a measure of how fluidy a fluid is. It's like how much information do you have to keep track of? How quickly does the gas or the fluid return to equilibrium after you perturb it? In the limit, as this Knudsen number is very, very small, the gas returns to equilibrium immediately. And so we only have to keep track of the density, temperature, velocity, and some other thermodynamic information. It's okay to exist at the level of thermodynamics instead of at the level of statistical mechanics. However, for our applications, like re-entry into the upper atmosphere, pick your favorite conical aerodynamics object, which is traveling at Mach 20 through the upper atmosphere, then the fluid dynamics equations are no longer sufficient. We need to resolve much more information about the gas. And in this case, we need a kinetic description, which is a statistical mechanics thing. We're going to keep track of the distribution function of the gas, which tells the density of particles at a given position with a given velocity, So this is microscopic information about each particle at a given time. And this is the quantity that we'd like to solve for. And I've put here, just for illustration, the kind of correct PDE which you would like to solve. So you can ignore all of this, except that the f is like a 7-dimensional function. All of these subscripts mean evaluating it at different points. And so you have this like ludicrously complicated 7-dimensional integral to do, 5-dimensional integral to do at each point of your domain. It's like a very complicated integral differential equation. And solving this directly is possible, but I don't really want to mess around with that. It's far too complicated and mathsy. So we instead introduce what I would like to think of as kind of the obvious simplification. If you're modeling a whole load of particles bouncing around, and you only want to extract some kind of coarse-grained average information, why don't we just represent like a few million of real particles, if there's 10 to the 23 particles? Why don't we represent a few million or billion of them with one simulation particle? And we say, okay, let's assume that all of these particles have roughly the same position and roughly the same velocity, and then we can hope to do something stochastic to to represent the physics and then extract flow quantities by averaging over these particles, or averaging over space, and then averaging over time to get something that's smooth and steady state. And this is kind of the easiest way of doing it. We first kind of turn the gas into discrete computational particles, or sample from a distribution function in like mathematical terminology, I suppose. And then we partition our spatial grid into fixed cells. And at each time step, we'll just randomly select pairs of particles uniformly to undergo collisions. And they will actually undergo a collision with a probability proportional to this kind of physical quantity sigma, which represents the physics of what's going on in the interaction. If they're accepted to undergo a collision, then we update their velocities and internal energies. And then after that has been done, we'll just update their positions with whatever their velocity is. And this turns out to be a very good kind of robust method. And so all we need now is like a model for this cross-section sigma. And there are lots of simplified models. The easiest one for monatomic molecules with no internal degrees of freedom, just a single atom like argon or something, is to say that the cross-section is proportional, is like a power law in the relative velocity. Excuse me. With this assumption, everything kind of becomes relatively simple in terms of selecting collision pairs. We're just going to assume isotropic scattering, like after you collide, then you fly off at some random angle, and everything's determined by conservation of energy momentum. But the key point is that we need to fit this omega parameter, which is the only free parameter, by fitting some experimental data. The experimental data in this case tends to come basically from the 70s, from the Apollo program, and it can be pretty unreliable or hard to obtain new experimental data if you want to do new calibration. So what's the alternative? Well, if you have, it would be kind of nice just to start with a model for the interaction between two atoms. So if you had a potential which was modeling the forces between two colliding atoms, that's a more desirable quantity to start with than some kind of top-down phenomenological model. But if you had this, then at first glance it looks like you would need to solve. Excuse me, that's a mistake. I need a sum here, wouldn't I? But you need to solve kind of a 6n dimensional Newton's equation, where n is the number of atoms in your gas. Like actually keeping track of where each atom is at each time, what its velocity is, whether it's interacting with any other particles. And even though there's lots of tricks to kind of make this faster, it's still roughly as computationally expensive as you would expect it to be if you're modeling, realistic number of atoms, which is extremely expensive. However, if we use kind of relatively simple interatomic potential like Leonard-Jones, which is like a mixture of polynomials, then we can get pretty good results matching to experiment. And this is kind of going to be like a nice high fidelity model to compare to. My favorite numerical method is kind of like halfway in between these two. So we had DSMC, which is like completely stochastic phenomenological models, molecular dynamics, which was resolving everything independently. And then we've got this kind of bastardized mixture of the both of them, which is called direct molecular simulation, just to be, take words from both. And in this case, we're going to select pairs to collide at random, just like in DSMC. So there's many, many fewer computational particles than real particles. But when they're accepted for a collision, then we're actually going to resolve the trajectory that those two atoms describe using some kind of integration procedure and the actual interatomic potential that we would use in molecular dynamics. And the advantage is that we require no modeling choices, and we also save huge amounts of computational cost versus molecular dynamics with the same accuracy in lots of aerodynamics applications. So this is a very desirable method, but it's still very, very expensive. So this is a picture maybe you should keep in your mind about this method, at least for a monatomic gas, is that when two particles are accepted to collide, we're literally just going to start one of them on the left, one of them at the right. They have a given relative velocity, and we select this initial separation distance at random, and then they're going to fly towards each other and then fly off. And then once we terminate this simulation of some cutoff time, then the output is this scattering angle chi. So all we need is a map between the energy or the relative velocity of these particles, the B, which is called the impact parameter, as another input. So it's a map from the energy of a collision and the impact parameter to the scattering angle. So this is like a one-dimensional function of two inputs. Feels a bit expensive to be doing loads and loads of time steps of some velocity integration scheme, maybe 50 or 100,000 time steps, just to get this one quantity of interest out the other side. So we would like to do some machine learning on it, just as an initial test case. So this is the function we'd like to learn for some idealized case. In practice, it gets very complicated down here in real simulations. But this doesn't look like too bad a function to learn. Sorry, I'll skip over this since I'm taking a bit too much time. But let me just skip straight to the machine learning and the results, perhaps. That I'll show you some aerodynamics kind of simplified test cases. The one which is the 1D shock, where it's kind of the simplest interesting case where you're very far out of equilibrium and at very high Mach numbers, but everything's one-dimensional, everything's kind of nice and well behaved. You know what the boundary conditions are, etc. So our machine learning problem is to reproduce this collision angle chi, given some trajectory data. So maybe we'll choose a neural network as our model, represent the scattering angle as a neural network. Here I've chosen to divide up the input regime to make it a bit easier to learn. And then if we train this offline on some data set, then it's good thing. We can get good results and we can get it at 1 order of magnitude improvement in computational time based versus the direct molecular simulation, which is quite good. So this is like maybe 20 minutes rather than 5 hours, which is good for like an engineering time turnaround point of view. So on the left, this is a good case where our dark line is our results and the crosses come from very, very expensive molecular dynamics. And you can see that we reproduce this, and it's not easy to do this. It's not easy to find a method which will reproduce it this closely. But what I didn't tell you was the data set, the training data set is selected from this case. And then when we go up to Mach 9, then we start to see some problems in the profile. And if we were to go up even higher or to different experimental conditions, these problems start to get worse. So our neural network can be good if it's trained properly, but it's hard to train properly. How are we going to make sure that we get the right data set? Well, let's generate the data set on the fly and then do the training kind of alongside the physics. So if we do that, we're going to just, for a very small subset of the computational time steps, do this very expensive procedure. And I've said 50,000 trajectories, which sounds like a lot, but if that's running on a GPU, that's going to be quite fast. And actually, we need tens of millions of trajectories over the whole simulation, even for a simple case like this. So it represents quite a good computational speed up. Just train the neural network during that time step, and then use the trained model, which may not be yet kind of fully trained, to evaluate the rest of the collision events that we need during that time step. I'll skip over the detail. Again, this is like for engineering audiences, my supervisor insists that we put in some equations, which, you know, apparently make it look very impressive, more impressive. But in any case, we train the neural network using gradient descent. And then we can get, for the cases I showed you beforehand, much better results. So the dots are our offline trained model. The red lines are like a standard DSMC model, which is the cheap model with kind of off-the-shelf parameters which haven't been calibrated. And all the dark lines are the 3 high-fidelity methods. So the fact that you can't make them apart is a good thing in this case. That these dark lines being on top of each other means that we're reproducing the high-fidelity data accurately. And if I go to some other, again, for engineering applications, this will be more impressive that this number here had changed, I promise. But we get kind of similar levels of accuracy, even for like ludicrously out of sample, high Mach number cases, which are kind of very difficult to resolve. And you can see that the standard method is quite badly wrong in these cases. So we're able to get this, this improvement in accuracy with a large computational speed up. But this is kind of a relatively simple test case. Unfortunately, you wouldn't typically want to just, we don't live in an atmosphere of argon, sadly. Well, I'm sure all the aerodynamics people would be much happier if we did, but we live in an air of nitrogen and oxygen. So instead of having one atom, we really need to resolve 4 atoms at the same time. 2 atoms for each interacting molecule. And then suddenly these molecules have much more degrees of freedom. So we previously had a function of 2 inputs with 1 output. Now we at least have a function of 4 inputs, which is the, the same energy and impact parameter, and then the 2 rotational energies of the 2 molecules, even if we ignore vibrational energies and quantum mechanics things. And we're going to have the output being the same scattering angle as before, and the 2 new rotational energies. Really, it's a function of 6 extra variables because you need to choose all of the relative angles to specify an initial configuration of the molecules as well. So this is the current larger problem which I'm trying to work on. Yeah, which would potentially have some real applications, even though we're neglecting vibrational dynamics, which apparently is okay. So my time is up. Thank you very much for listening, and I appreciate any questions you might have.